Welcome back to another explainer. I am absolutely thrilled you're joining us today because we are going to completely reframe how you think about the single most common substance on Earth. I mean, we drink it, we swim in it, we are fundamentally made of it, but behind this seemingly simple, everyday liquid lies a massive, mind-bending scientific mystery. Today, we're unpacking the groundbreaking research that proves water is much, much weirder than we ever thought possible.
Okay, let's dive into this. There's this famous scientific quote that just perfectly sets the stage for what we're talking about today. It goes, "All liquids on this planet behave in a similar manner, and then water completely misbehaves. It's like a child that you cannot control." And it's so true. Water is nature's ultimate rebel. Think about normal liquids for a second, things like oil or alcohol. They all follow the standard, predictable rules of physics. If you take a glass of liquid alcohol and freeze it, the frozen pieces become denser, they get heavier, and they sink straight to the bottom. Simple, right? But water? Water completely misbehaves.
Let's look at a quick rap sheet of water's crimes against physics. First off, solid ice floats. As water cools down, it actually expands instead of contracting. And bizarrely, it hits its absolute maximum density at exactly 4 degrees Celsius. Now you might be thinking, okay, cool, that's some quirky trivia for my next pub quiz. But no, these specific anomalies are absolutely crucial for your existence. Because ice floats, it forms this protective thermal blanket on the surface of oceans and lakes in the winter. That stops the bottom from freezing solid, which allows marine life to actually survive. And because water is densest at exactly 4 degrees, it creates this massive vertical circulation in the ocean, churning vital nutrients from the surface all the way down to the depths. It even gives water this incredible capacity to hold on to heat. I mean, that's what allows the Gulf Stream to carry warm Caribbean waters all the way across the Atlantic to stabilize Europe's climate. If water acted like a normal liquid, life on Earth literally wouldn't exist.
And the weirdness definitely doesn't stop there. Have you ever actually stopped to wonder why ice is slippery? For the longest time, people just assumed it was the pressure of an ice skate melting the ice, or maybe friction creating heat. Actually, scratch that. Those theories don't explain why you can just stand perfectly still on ice in regular shoes and still slip and fall. Recent research finally solved this, and it brings us to a really fun analogy: the wobbly two-footed bar stool. At the very surface of a block of ice, the water molecules are exposed. They don't have enough neighboring molecules to bond with on all sides, so some of them are stuck making just 2 connections to the ice below them. Imagine having a couple of drinks and trying to sit on a bar stool that only has 2 legs. It's incredibly unstable, right? You're going to wobble. Well, these wobbly water molecules easily tilt, detach, and roll all over the surface like microscopic, lubricating marbles. When you slip on ice, you're literally rolling on top of a layer of unbound, tumbling water molecules.
So why does water behave so erratically? Well, back in the early 1990s, a group of scientists in Boston ran massive computer simulations of thousands of water molecules to try and figure this out. And they proposed this crazy, completely radical idea called the two-liquid hypothesis. They suggested that deep down, water isn't just one liquid. It's actually 2 totally different liquids existing at the exact same time, constantly fluctuating back and forth. To really wrap our heads around this, let's picture 2 completely different environments. On one side, we have low-density water. Imagine a spacious, highly organized, fancy restaurant. People are sitting quietly at their tables, everything is orderly, and they're taking up a lot of room. This represents cold water locking into an open, airy structure. On the other side, we have high-density water. Imagine a compact, totally chaotic dance floor where everyone is bumping into each other and moving fast. This is the tighter, warmer structure. What we call ordinary water is actually a constantly shifting, microscopic dance between these 2 states.
Now, the two-liquid hypothesis perfectly explained water's weird behavior on a computer, but actually proving it in real life, yeah, that was a totally different story. To prove this hypothesis, physicists like Anders Nilsson knew they had to study water at incredibly cold temperatures, well before it crystallized into normal, everyday ice. And that led them to study a bizarre, completely alien state of matter known as amorphous ice. By crushing and cooling water down to a mind-numbing -200 degrees Celsius under extreme pressure, the normal crystal structure just completely collapses. It becomes this disordered state that acts like a highly viscous, slow-moving liquid glass. It's essentially trapped, having completely lost its ability to flow.
Which brings us to a massive structural roadblock, and arguably one of the greatest scientific detective mysteries of our time. How on earth do you take a picture of a liquid before it freezes? Water molecules shift their positions in less than a trillionth of a second. Imagine trying to photograph a ghost that completely vanishes the exact microsecond you turn on the camera flash. If you try to warm up that super-cooled amorphous ice just enough to see the 2 liquid phases, it almost instantaneously flashes into ordinary crystal ice. The stakes here were incredibly high. Decades of fierce, heated debate in the scientific community rested entirely on capturing an image of something that essentially disappears the moment you try to look at it. Now, what's really interesting about this whole setup is the sheer jaw-dropping scale required to pull off this scientific heist. To catch this vanishing liquid, Nielsen's team needed some incredibly heavy machinery. Specifically, the SLAC facility at Stanford University, which houses a massive 3-kilometer-long particle accelerator. They use this gigantic underground tube to generate X-ray flashes that last for just a fraction of a trillionth of a second. Imagine having to fire that microscopic, impossibly fast camera flash at ultra-pure, super-cooled water droplets that are completely invisible to the naked eye, hovering in a vacuum at minus 45 degrees Celsius. The contrast between this gigantic, roaring piece of machinery and those delicate, microscopic little droplets is just incredible.
But as any researcher will tell you, science is rarely easy, and it is almost never right on the first try. The journey to capture this image was a grueling, globe-trotting process of trial and error. Attempt number 1 at Stanford. They fired the X-ray laser at those minus 45-degree droplets, and it completely failed. They only saw one phase of water. Attempt number 2 involved packing delicate samples under immense pressure in Sweden, but the slightest, tiniest bump during transport caused the supercooled liquid to instantly crystallize into boring, normal ice. Ruined. Finally, years later, a brand new, state-of-the-art X-ray facility opened up in Pohang, South Korea. The team packed up their minus 200-degree glassy ice samples, flew all the way across the world, and held their breath for attempt number 3.
Let's walk through the exact methodology they used in South Korea, because it is brilliantly complex. Step 1. They take that ultra-thin, millimeter-sized ring of glassy, amorphous ice sitting at minus 200 degrees. At this point, the molecules are completely stuck in place. Step 2. They zap it with an incredibly powerful, concentrated infrared heat pulse. This essentially shock heats the glass, rapidly unlocking the frozen molecules and forcing them to wake up into a liquid state as they expand toward normal room pressure. Step 3. Before the water can even figure out what's happening and turn into normal ice, they instantly fire the X-ray laser, capturing a picture of the molecular structure on a detector screen in a matter of nanoseconds.
Let me set the scene for you in that control room. The scientists are huddled around the monitors, just agonizingly waiting to see what shape the X-rays will make on the detector. If they see one curve, it's one liquid. If they see scattered dots, it failed and turned into ice. But if they see 2 rings, that's the holy grail. That means 2 liquids. Okay, the laser fires. 10 nanoseconds after the heat pulse, on the monitor shows one bright, narrow curve. Just one liquid. Hard sink. But wait, they fire again. 100 nanoseconds, a faint second ring starts to appear right next to the first one. The structure is physically separating. They fire again, 3,000 nanoseconds, and that second ring is glowing brightly. Boom! Right there on the screen, in real time, they had visual, undeniable proof that the 2-liquid phase transition was absolutely real. That single breakthrough completely rewrote our fundamental understanding of physical chemistry. But to really grasp the real-world implications of this, consider the staggeringly massive number of 55 billion. In Switzerland, a researcher named Sylvie Roque was studying how water reacts to electrical charges. She introduced a single charged molecule, just one tiny little ion, into a pool of pure water. And what she found was staggering. That one single charged molecule instantaneously altered the orientation and correlation of 55 billion surrounding water molecules. Just let that sink in. One single change, instantly rippling out to affect 55 billion neighbors.
And this brilliantly illustrates our next massive leap in understanding water. For decades, we've thought of water in biology as just this passive background, a solvent, basically a dumb bathtub that our complex DNA and proteins just happen to float around in. But this new research suggests water is actually the matrix of life. Because of those unique hydrogen bonds, and because a single charge can instantly align billions of molecules over massive distances, water might actually be actively mediating communication inside our cells. Think about it. The constant, rapid-fire fluctuation between those high-density and low-density states, the dance floor and the restaurant tables, those could literally be acting as digital ones and zeros, passing complex information from one side of a living cell to the exact opposite end in picoseconds. Which brings us to our final, entirely mind-bending question for the day. Is water actually the biological computer network of nature? We always look at DNA as the master instructor of life. But what if water is the invisible, high-speed internet that actually makes the whole shebang function? The liquid that makes up over 60% of your body isn't just some simple mix of oxygen and hydrogen. It's a fluctuating, highly communicative, two-phased rebel of physics that actively sustains every living thing on this planet. So, the next time you grab a glass from the tap and take a sip, just remember, you are drinking nature's most intricate, chaotic, and mysterious masterpiece.
Keep learning, keep questioning, and I will see you in the next explainer.